In this video, I want to go over a little bit of the basics of number theory. And number theory is just the mathematical word for really, in essence, talking about the divisibility properties of numbers and the things you can glean from those. We're doing this so that we can talk about something called mathematical induction, which is another proof technique that's really useful and I think really fun as well. But we need a little bit of background so that we can prove some results using mathematical induction. And one of the best ways is in terms of number theory. And we're going to be using this kind of throughout the course. This stuff will come back over and over again. And whenever we're talking about the divisibility of numbers, if it's not said otherwise, we're assuming these numbers are integers. So the first thing I need to talk about are a few definitions. So the first thing I need to talk about is what it means for a number a to divide a number b. Well, we say a divides b, and we write it like this. So we can think of this symbol here as divides. Or if you like, another word, you could, or another phrase is a factor of. So a divides b. If there's an integer c, that's some other integer, or you can write b as a times that other integer. And there's other ways of saying it. Of course, we can say b is divisible by a, or b is a multiple of a. Anything like that is good. And just a few quick examples just to make sure we understand what's going on. We've talked a little bit about divisibility, but we haven't used that word. We were talking about even and odd numbers. And even numbers are numbers that are divisible by 2. So something like this, 2 is a factor of 18, since 2 times 9 equals 18. So we're thinking of this as our a in that definition. This is our b. So b, here's our a. And our c, the number that you multiply 2 by to get 18, that's our c here. In this case, it's 9. And that's how divisibility works. And if something isn't divisible, so let's say, for example, 4 isn't a factor of 13, so to say it's not, we just put a little cross through the divide symbol. So 4 doesn't divide 13. So that's our first definition. Our next definition has to do with something called a linear combination. We say some integer n is a linear combination of two integers, exactly when or if and only if there are two other integers, x and t, so you can write n as a multiple of a, so x times a plus a multiple of b, y times b. Let me kind of show you what I mean. So we can say 1 is a linear combo, so linear combination of, let's say, 2 and 3, since we can write 1 as, well, maybe pause the video and think about what multiples of 2 and 3 you need to make, or I should say take, so that you can make 1 out of it. It should be quite easy. Well, all you need to do, you need to take -1 times 2. So our x in this case is -1, and we're taking 1, 3. So our y is 1. So we can write 1 as a linear combination of 2 and 3. And we'll talk about these in more detail going forward. So let's talk about a few results here. The first one, and this is going to be really important, so if a divides b, then a divides n times b for all integers of n. So to reword that in kind of language we've previously used, well, A is a factor of, if A is a factor of B, then A is a factor of any multiple of B. So, using our definition, remember what it means to be a factor of a number or to divide a number. See if you can prove this. Pause the video now and try this. Okay, let's go ahead. And again, we're assuming all of our numbers are integers, so we're not going to write that anymore for this section. So here's our proof. Let's let A be a factor of B. So what does that mean? So that means B equals A times C for some integer C. Okay, that's great. That's what we know. And we need to show that A divides n times B, which means we need to show that n times B equals A times some integer. And again, this looks very similar to where proofs if numbers are even, because if you think about it, even just means divisible by 2, or 2 divides that number. So we're just not using 2 now, we're using some other number, A. Okay, so let's go ahead. Let's consider n times B. But we know B equals A times C. And of course, well, we just need to do a little bit of rearranging using the commutative property. So this equals A times N times C. And let's put this in brackets. And there we go. We have A times some integer. So since N times C is indeed an integer, the product of two integers is an integer, then A is indeed a factor of N times B, because we wrote N times B as A times some integer. So that's example 24.1. Let's try the next one. Let's try 24.2. So if you have a number n and it divides A, another number n that divides B, we need to show that n divides a linear combination of A and B. So let's see if we can do that. Again, pause the video and try that. Okay, now that we're back, again, let's set it up. So our proof, let's let n divide A and n divide B. So what does that mean? That means that we can write A as n times, let's say, C, and we can write B as n times D for some CD that are integers. Okay, that's great. And of course, we need to show that we can write x times A plus y times B as n times some integer. So that's our goal here. So we'll do the same thing. Let's consider x times A plus y times B. And we know some things about A and B. So let's go ahead. So we know A equals n times C. And again, these brackets aren't doing anything mathematically, but they are showing the reader that I'm replacing A with n times C easily. So it's easy for the reader to follow along. And we can replace B by n times d. And hey, look, we have a factor of n in each number. So let's factor it out. So we get n, and we're left with times xc plus yd. So we've written x times a plus y times b as n times some integer. X times c plus y times d is an integer, so we've done it. So let's just tell people that. Since xc plus yd is indeed an integer, then we have that n is a factor of a x, or xa it's written, so I might as well write it the same way. xa plus yb, and we're done. And I'll put a little square up here as well, because I forgot to do that last time. You can either color it in or leave it as a white square. It means the same thing. All right, so let's look at this example. We want to show that 1 is a linear combination of 7 and 5, which means, what does this mean? There exists two integers, say x and y, where if I take 7 times x and add it to 5 times y, I get 1. So see if you can figure this out. Okay, now that we're back, well, maybe you realized that 7 times 2 is 14, and 5 times 3 is 15. So if we took, let's say, 15 and subtracted 14, or added negative 14, so maybe let's make this a negative 2, and this would be a negative 14, then we would get 1. So we get that 1 is indeed negative 2 times 7 plus 3 times 5. Negative 14 plus 15. That's our linear combination of 7 and 5. Maybe you didn't do that. Maybe you found another one. Just because there is 1 doesn't mean that there's only 1. In a lot of cases in linear combinations, it can be done in more than one way. So maybe instead of that, you've noticed that 7 times 7 is 49, and 5 times 10 is 50. Maybe you noticed that. So again, we'll do the same thing. You could take negative 7 sevens and 10 fives. So 1 is negative 7 times 7 plus 10 times 5. Or maybe you noticed another one. There's even more. Maybe you took 7 times 3 is 21, and 5 times, well, let's say, negative 4 is negative 20. So you can take 3 sevens and negative 4 fives. There's loads of ways of doing this. So 1 equals 3 times 7 plus negative 4 times 5, or countless other ways. But here are 3 examples that you might have thought of yourself. A few small but very important notes here. And the first note I want to make is that 1 divides every integer. So 1 is a factor of n. Let's even say for all n, 1 is a factor of n, since you can always write n as n times 1. Or maybe I'll write it as the other way around, 1 times n. We're thinking of this as our, if this is a divides b, here's our b, here's our a, and here is our integer c that I multiply 1 by to get b, which is n. So this works for any number. That's the property of 1. But n isn't a factor of 1 for all n not equal to, let's say, plus or minus 1, I guess. Maybe I'll put a plus minus here. And same here. Okay. So 1 divides everything, but is divisible by basically nothing. Let's consider 0 now. So 0 is a multiple of every integer. So that means that every integer for all n is a factor of 0, since we can write 0 as, or I should say equals, n times 0. So for any integer you like, you can write 0 as n times it, because 0 times anything is 0. So every integer is indeed a factor of 0, or you could say 0 is a multiple of every integer, or every integer divides 0. But besides 0, so for all n not equal to 0, 0 isn't a factor of n. Since we can't write n as 0 times c for any c, unless n is 0. Because remember, 0 times anything gives a 0, and if n isn't 0, well, we're not going to get 0. So the best way to think about it is 1 divides everything, 0 is divisible by everything, and 1 is divisible by basically nothing except itself. 0 divides nothing except itself. So let's try this one. Let's try example 24.4. So it's basically saying if 2 is a factor of n squared minus 1, or you could think of it as if n squared minus 1 is even, then n squared minus 1 is divisible by 4. That's pretty interesting. Let's see if we can prove that. So, okay, we're going to use a little sub-result. We call it a lemma. It's just a little proof that is used in another more important proof, or another bigger proof, I guess. So let me write down the lemma that we're going to need. And it's going to be a little small one. In fact, I'll leave it as an exercise. It's so easy. And it's if n squared is odd, then n is odd. And I'll give you a hint for the proof. Do one by contraposition. I think that's easy enough. I can leave it as a little bit of an exercise. If you're not sure, you can always contact me and we can talk about it a little more. But that's what we're going to use. Okay, so let's go ahead and talk about this. Okay, so let's assume the if part is true. Let's assume that 2 is indeed a factor of n squared minus 1. Well, what does that mean? That means that we can write n squared minus 1 as 2 times c for some integer c. And then it follows that if we add 1 to both sides, that n squared is 2 times c plus 1. So what do we have here? We have that, well, n squared we wrote as 2 times an integer plus 1. So n squared is odd. That's the definition of an odd number. So we have n squared is odd. But we have this lemma. If n squared is odd, then n is odd. And you should be able to do this exercise, so we'll say that this is true. If n squared is odd, then n is odd. So by the lemma, we have n squared is odd, so we know n must be odd. By the lemma, and usually, I'll talk about this for a second. Usually we'd have some sort of reference here, so we might call it lemma 1, or depending on the chapter, maybe you'd have it in terms of chapter, so lemma, 4.1 or something like that. So if there are numbers to go with your results, you would reference those results. But this lemma is kind of internal to our example, so I can just say by this lemma, we know n must be odd. So if n is odd, thus we can write n as 2 times some integer, let's call it d plus 1, for some integer d. Okay, so that's all from the assumption here. So we've used our assumption and we've deduced that n must be odd. If 2 is a factor of n squared minus 1, we've deduced that n must be odd, and we're asked to show that n squared minus 1 is divisible by 4. We can write it as 4 times some integer. So let's do it. To show, we want to show that n squared minus 1 is 4 times some integer. Let's go ahead and do it. So let's consider n squared minus 1. But we know n is 2d plus 1. So it's 2d plus 1 squared minus 1. And if we expand that out, which I'll leave for you guys to check, I'll just write down what it is. We get 4d squared plus 4d plus 1 minus 1, which simplifies to 4d squared plus 4d. And hey, look, just like we expected, our terms left over here have a factor of 4. Let's factor that out. So this is going to be 4 times d squared plus d. So we have 4 times some integer. D times d plus d is an integer, since d is an integer. So since d squared plus d is indeed an integer, we know that 4 is indeed a factor of n squared minus 1. And we're done. So this is one way of proving it. I'm sure there are other ways of going as well, but I like this way because it gets us to use a little lemma here. This is very similar to I think it was topic 11, we proved that if n squared is even, then n is even. So you can imagine if n squared is odd, then n is odd, being a very similar idea. And the key is how I thought about this. Well, I wanted to show that n squared minus 1 equals 4 times something. So I need to get some 4s in there. If I just replaced n squared with 2c minus 1, well, that gets me nowhere. I'll just get n squared equals 2c. And that won't do anything. Or 2c plus 2, whatever. But, no, it would be 2c. It would be 2c. So I'm thinking, how can I get this 4 in here? Well, I know that if I had a 2 squared, I'm thinking I have the squared here, so I might be able to use that. I will get some things that have factors of 4. So if I can reason something about n, if I can write n as an odd number, then that'll do it for me. So that's why we're using this lemma. We know n squared is odd, so that tells me that n is odd, so I can write n as an odd number. And then when I square n, which is 2d plus 1, then I get my 4s I can factor out. So that's how I thought about doing this problem. Let's look at one more. And that one is as follows. So if A isn't a factor of B times C, then we have that A isn't a factor of B and A isn't a factor of C. So pause the video now and see if you can prove this. Think about what proof technique, whether a direct proof, a contrapositive proof, or a contradiction proof would be the most appropriate. Okay, now that we're back, let's look at this result. It's saying A doesn't divide BC, then A doesn't divide B, and A doesn't divide C. The way I'm thinking about this is it's hard to write down that one number doesn't divide another. You can do it with something called the quotient remainder theorem. You just put a remainder rather than just saying you can write BC as A times some number. If it's not divisible, you say BC is A times some number plus a remainder. So it could be done like that, but it gets a little complicated. It's very easy to write down that A is a factor of BC, A is a factor of B, A is a factor of C. So I think the way to go is a proof by contraposition, because then we'd write down if A divides B or A divides C, because remember with De Morgan's law, if we're taking the negation of a joined statement with an and or an or, we need to flip the joining word. So the and becomes an or. So we get if A divides B and or A divides C, A divides B or A divides C, then A divides BC. So let's do that. Let's prove this. And let's do it by contraposition. Okay, so we're going to assume the then part is false, show that the if part must be false. So assume that, well, it's not true that A doesn't divide B and A doesn't divide C, so that means that A divides B or A divides C. So remember, that's the negation of this here. Now, if we look at what we want to show, that A divides BC, because we want the negation of this, because we're doing it by contraposition, B and C play the same role here. So it's just the product of these two numbers. There's no order to product. So I'd be doing the exact same work if I assume A divided B or if I assumed A divided C. So this is a good opportunity to use without loss of generality. So without loss of generality, let A divide B. Then what does that mean? Well, we can write B as A times C. We're already using C, so better not use that again. Let's use K, I guess, for some integer K. And we want to show that B times C equals A times some integer, because we want to show that A is indeed a factor of B times C. This one will be pretty straightforward. So if you haven't tried this and gotten it yet, this is a good time to pause the video and try it from here. All right, let's consider B times C. Well, we know B equals A times K times C. And remember, what did I do here? I just knew that we said that B equals A times K by assumption, so I substituted in place of B, A times K. And we just have three numbers multiplied together, so let's use the idea of associativity and just bracket things the other way. A times K times C. And look at this. since k times c is an integer, two integers multiplied together give you an integer, our result is true. We have that a is a factor of b times c, and we are indeed done. So that's a little introduction to number theory, and we're going to use these results going forward, especially when we do some examples of mathematical induction, and afterwards as well. This stuff will come up throughout the course.